The comet's sundering unfolded somewhere beyond the quiet boundary, where sunlight fades into the deeper cold, but no one witnessed the moment. No spacecraft caught the turning of its fractured body. No telescope recorded the shedding of its mass. Across the darkness, 3 Atlas split in absolute silence, and yet the cosmos left no trace of violence, no plume of dust, no glimmer of drifting shards, no delicate veil of pulverized ice. It was a shattering without shatter, a wound without debris, a cosmic rupture that defied the very vocabulary astronomers have cultivated to describe the disintegration of fragile celestial wanderers. The mystery began as a whisper in the data, an anomaly, only detectable once the light curves were studied carefully. Something had separated, but nothing around it spoke of ruin. In the history of solar system comets, fragmentation is an act marked by drama. A cloud of particles erupts, forming luminous tails, broadening halos, and expanding arcs of material that blush against sunlight. These events leave scars across space ribbons, threads, and fountains of dust, pushed outward by the breath of the star they approach. But here, for this object drifting in from the interstellar deep, the universe seemed to break its own rules. It allowed a body of ancient ice and rock to come undone with a precision so immaculate that even the instruments designed to sense the faintest speck found nothing at all. Such silence carries weight. It evokes the same unease that arises when a familiar pattern is suddenly interrupted. Comets behave in ways humanity understands intimately. They are frozen relics, volatile, vulnerable, sculpted by sunlight, and spun by invisible pressures. The scripts of their lives and deaths are etched into the archive of astronomical observation. But 3i Atlas did not follow any script. It broke apart as though performing for forces unknown, slipping into 2 distinct forms without the expected cascade of microscopic ruins. It behaved as though trying not to be seen, preserving its own secrecy even in destruction. The absence of debris becomes in this context the loudest element of the event. Silence turns into signal. Like the missing echo in a dark chamber, the lack of particulate trails reveals something about the very act that produced it. Fragmentation without fragments is not simply unusual, it is a contradiction of thermodynamic intuition. It invites questions that reach into the heart of planetary science. What does it mean for an object to split cleanly? How can a structure as fragile as an interstellar comet, formed under the gentle assembly of distant starlight shaped by eons of cold, separate without collapsing into chaos? In moments like this, astronomy steps into a philosophical space. The discipline, though grounded in physics, often brushes against the intangible. It concerns itself with things that existed long before humanity and will persist long after it. 3i's Atlas is one such thing. Born around another star, nurtured in a different cradle of cosmic chemistry, it carried with it the story of a distant system, a place whose sun may have brightened or died long before the first humans looked upward. As it crossed into the solar system, it became briefly illuminated by our star, offering a rare glimpse into the geology and structure of matter shaped outside our cosmic neighbourhood. And in that brief window, it performed an act no one had ever recorded. The silence surrounding the act becomes a metaphor for the interstellar visitor's deeper enigma. A fragmenting comet is expected to speak through its dust, to reveal its internal composition like a book forced open. Scientists hope for this because every particle tells a story: molecules trapped in ice minerals compressed by ancient collisions, organic compounds weathered by cosmic radiation. Instead, 3i Atlas divulged nothing. It held its secrets close, shedding no samples, offering no tastes of its chemistry, no drifting breadcrumbs for spectrometers to chase. It fractured cleanly and continued onward, leaving only uncertainty in its wake. There is an elegance to this kind of mystery. It resembles the quiet tension of a paradox in nature, a phenomenon that feels simultaneously gentle and unsettling. Even the motion of the 2 fragments after separation appeared measured, deliberate, devoid of chaos. The universe rarely offers such restraint, especially in objects so susceptible to heat stress and rotation. Most cometary breakups unfold through violent asymmetry. One section ruptures first, unleashing jets that tear the rest apart. Dust follows like the unravelling of fabric, but here nothing frayed. This impossibility draws the mind toward the broader challenge of interstellar science. Humanity encounters these objects only rarely. Before 3 Atlas came Basostin. Oumuamua, a body whose strange, tumbling shape and non-gravitational acceleration left scientists debating for years. With those two visitors alone, the known population of confirmed interstellar objects remains sparse. Yet even in this tiny sample, anomalies dominate the narrative. Both arrivals behaved unlike any local comet. Both raised questions that resisted easy explanation. Both hinted that the material drifting between stars may follow rules that diverge from the familiar rhythms of our own system. Thus, the silent shattering of Three-Eye Atlas becomes more than a singular event. It becomes a symbol of the unknown architecture of the galaxy. Somewhere in the cold void between suns, comets form under pressures and influences Earth-based instruments have not yet imagined. They may harbour voids, crystalline structures, layered chemistries or energy-trapping configurations unknown in local objects. They may have histories involving near passes with other stars' collisions with exotic bodies or environments whose temperatures and radiation fields differ dramatically from those around the Sun. And when they fracture, those histories manifest in ways that challenge terrestrial intuition. In this sense, the breakup of Three-Eye Atlas is the opening note of a longer, more intricate narrative. The absence of fragments becomes the gateway to an investigation that stretches across disciplines: astronomy, physics, chemistry, thermodynamics. It forces researchers to confront their own assumptions about the fragility of icy bodies. It invites speculation about unseen forces that govern the internal behaviour of materials forged far from Earth. And most of all, it humbles the scientific mind, reminding humanity that its understanding of the cosmos is still young, still incomplete, still susceptible to quiet astonishment. As the fragments drifted along their paths, the universe seemed to murmur a reminder not every rupture leaves ruins. Some fractures are too clean, too controlled, too precise to align with established frameworks. These events act like cosmic riddles carved into the darkness, urging observers to revisit assumptions and question the boundaries of the possible. The silent shattering of Three-Eye Atlas marks the beginning of such a riddle, one that will unfold across instruments, theories, and decades of contemplation. The break itself is only the first thread. What follows is the attempt to unravel the forces behind it, to understand how something so ancient and fragile could divide without revealing the faintest trace of its undoing. The first detection came not with the flourish of revelation, but through the steady discipline of survey astronomy, where each night the sky is swept methodically frame by frame in search of wandering objects. In the dry stillness of the desert, where heat fades into cool air and stars sharpen against a deepening vault, the Atlas survey scanned the heavens with the patience of a watcher accustomed to incremental discoveries. It was here in this routine choreography of automated telescopes that Three-Eye Atlas emerged from obscurity, an anonymous point of light, faint but insistent, drifting across images separated by minutes, then hours, then days. No one knew in that unassuming moment that this would become the second confirmed interstellar object ever discovered. The data appeared ordinary at first, a moving point, with a trajectory that needed refinement. Astronomers at the University of Hawaii's Asteroid Terrestrial Impact Last Alert System catalogued it, marked its motion, and fed its coordinates into computational frameworks that determine orbital patterns. Even before human eyes examined the detection, the algorithms began to assemble meaning. A preliminary arc was constructed and something unusual surfaced within hours. Its path did not belong to the Sun. Such revelations require caution. When astronomers first calculate hyperbolic orbits, they know the sky can mislead. Poorly constrained observations, glints of noise, or transient instrumental quirks can mimic the mathematical signs of an object unbound to the solar system. But as more data accumulated, a shape emerged in the numbers. Night after night, the trace of the object grew longer, and each extension strengthened the conclusion this wanderer was not born here. Its eccentricity, the measure separating a bound ellipse from an open curve, grew steadily beyond the threshold of no return. It was on a hyperbolic path not captured by the Sun's gravity, but merely brushing past it in transit. Only then did astronomers begin to look closely at the object's brightness. Its colour profiles the rate at which it brightened as it approached the Sun. These patterns suggested a comet, not a bare asteroid or an inert shard of rock, but a volatile body awakening under the rising warmth of transit. Gas appeared to be escaping, lifting subtle signatures into the light that telescopes could detect. This was not unexpected. Comets, especially interstellar ones, often contain frozen gases that begin to sublimate even at enormous distances. What drew interest was the consistency of the emission. Everything seemed smooth, predictable, almost too stable. The wider astronomical community soon took notice. Observatories across the world contributed follow-up data, adding precision to the trajectory, refining the comet's speed, and mapping its inbound course. With each updated observation, the object's origin grew clearer. It had come from far beyond the planets, drifting across interstellar space for unknowable eons before passing into the reach of the sun's light. Its arrival was a rare opportunity, one that could illuminate the chemistry of distant systems, the physics of cometary interiors shaped elsewhere, and the diversity of bodies travelling between stars. Astronomers remembered what had happened with the first interstellar visitor Oumuamua. That detection had been fleeting and perplexing, revealing an object whose shape, motion, and behaviour challenged expectations. 3i Atlas offered the chance to learn more, to see whether interstellar visitors followed a pattern, or whether each represented a distinct chapter of galactic wanderings. With this anticipation came a sense of optimism. Here was an object producing a visible coma interacting with sunlight in measurable ways. Where Oumuamua had offered scant material for study, 3i Atlas seemed poised to deliver more. The data flowed in. Astronomers plotted light curves, watching the brightness rise as the comet warmed. They tracked its coma, its diffuse halo of gas, which broadened gradually. They measured its colour index, noting subtle shifts that hinted at its surface composition. It looked in many ways like a classical comet, an icy traveller responding to solar heating in familiar patterns. But beneath this veneer of predictability lay the first hints of strangeness. The rate of brightening was inconsistent with the expected mass. The coma appeared weaker than models predicted for a comet of its apparent size. The dust signature, usually visible even at great distance, seemed strangely muted. At this stage, no alarm was raised. Comets vary widely in their behaviour, and interstellar ones may behave differently still. Variance was expected. But the seeds of the mystery were already present, quiet but undeniable, waiting for the right observational angle to bloom into confusion. As the weeks passed, the comet moved inward, and astronomers prepared for a window of greater clarity. Spectral lines emerged from the gas it exhaled, allowing chemical identification traces of carbon-based molecules, icy compounds, and the sorts of volatiles expected from a cold-body visitor. Everything seemed to align with the portrait of a dormant relic stirring under a newborn sun. Then, in a series of observations spaced days apart, the object's signature changed. Its brightness plateaued unexpectedly, then shifted in a manner consistent with elongation. Telescopes sensitive to fine motion detected small but noticeable deviations in the point spread pattern. These were the first clues that the comet might have fractured or rotated into an asymmetric shape. Researchers requested more observations. The Minor Planet Center issued updates, triggering a global alert to any observatory capable of catching the faint visitor. When the new data arrived, it contained the revelation hiding beneath the earlier anomalies. The comet was no longer singular. It had become two. Even at this moment, scientists expected certain things. Fragmented comets throw off dust. They shed trails. They leave clouds of microscopic debris that reflect sunlight and create distinct brightening events. But the frames showed none. Between the fragments lay emptiness, clean, unblemished, untouched. The discovery that the comet had split came not from the chaos normally accompanying breakup, but from subtle divergences in the measured positions of what should have been one point of light. The discovery was clinical, mathematical, almost reluctant. The Desert Survey had found the visitor. The world's telescopes had traced its approach, and now they faced a puzzle stranger than its origin. The comet had broken, perfectly silently, leaving not a trace of the violence that should have accompanied its division. From that moment onward, the investigation shifted. The question was no longer, what is 3i Atlas, but how did it divide without leaving a trail? The discovery phase, so rich in observational detail, had laid the groundwork. Now the mystery would deepen, revealing contradictions that challenged comet science at its foundation. The realization did not arrive with a single undeniable photograph, nor with the crisp clarity of a resolved shape. Instead, it slipped quietly through the mathematics, through subtle deviations in the comet's predicted path that refused to align with expectation. Astronomers had grown accustomed to refining the positions of interstellar visitors with each new observation, but the adjustments required for 3i Atlas began to drift in opposite directions. as though two bodies rather than one were tugging against the model. At first, these deviations could be dismissed as noise, but when independent observatories reported the same irregularities, the pattern hardened into fact what the world believed to be a single interstellar traveller had split. This moment should have been accompanied by unmistakable signs. Fragmentation, especially in comets, is an act of violent exhalation. Gas erupts from cracks, ice sublimates explosively, dust billows outward in glittering arcs pushed gently into halos that glow under solar radiation. When a comet breaks apart, it does not do so quietly. It rips itself open from internal stresses, leaving a visible trail of its lost mass, scattered behind it like fine sand spilled in slow motion. Scientists expected exactly this, a wake of particulate matter drifting along the comet's trajectory. But nothing appeared. The first high-sensitivity images targeting the region between the two emerging fragments revealed a dark, empty gulf. No plume, no dust halo, no broadening of the coma. The space between them was cleaner than the surrounding sky, almost austere in its emptiness. This absence stood in direct opposition to the physics that normally governs cometary fragmentation. It was not merely unexpected, it was unsettling. The strangeness deepened when astronomers analysed brightness profiles. A fragmenting comet typically brightens. The sudden exposure of fresh ice, the kinetic grinding of internal materials, and the liberation of volatile compounds all contribute to an increase in reflected and emitted light. Instead, 3-eye Atlas dimmed slightly, as though the breakup had been an energy-neutral event, one that neither sprayed nor shed anything detectable. It was at this moment that scientists began to confront the possibility that they were witnessing a form of fragmentation that had never been documented. The theories that normally explain how a comet can break thermal stress, rotational overload, tidal forces were each confronted with an inconsistency. Thermal breakup should produce dust. Rotational failure should scatter debris radially. Tidal disruption should tear the body into asymmetrical pieces accompanied by fan-shaped outflows. But none of these signatures were present. The phenomenon began to resemble a paradox wrapped in observational silence. If the comet had indeed broken apart, something had absorbed or suppressed the very processes that give such events their characteristic signatures. This suggested one of two things. Either the breakup mechanism differed fundamentally from known cometary physics, or the fragments somehow avoided generating debris at all. The difficulty lay in accepting such a premise. Comets are fragile by nature. Their bodies form from loosely bound mixtures of dust, ice, organics, and void space, an architecture so porous that fragments should crumble under the slightest stress. A clean separation contradicts this softness. It implies an underlying coherence, a structural unity that would enable the body to divide along a plane with minimal material loss. But comets, particularly interstellar ones, are not expected to have such refined structural integrity. The contradiction deepened further when scientists compared pre- and post-split mass estimates. The total brightness of the object did not match the sum of the fragments precisely. It suggested that mass had been lost, yet this missing mass had left no trace. If material was shed during the breakup, it must have been in a form invisible to the telescopes scanning for particulate matter. Thus emerged a scientific riddle, a comet that split without producing anything detectable from the act. The moment this realization took hold, astronomers found themselves confronting an uncomfortable question. Had the event truly been a breakup, or could another process mimic the appearance of fragmentation? Some speculated about aligned fragments that had always been separate, merely drifting into detectability. But their divergent trajectories argued against this. Others wondered whether the comet had shed only microscopic gas phase material, but spectrometers showed no increase in gas density. Every alternative explanation collapsed under scrutiny. The shock rested not only in what was observed, but in what was not. Astronomy has tools designed to extract meaning from faint signals. Instruments can detect dust so thin it resembles smoke. They can sense gas emissions weaker than the breath of slowing sublimation. They can resolve trails that disperse across millions of kilometers, and yet the space around 3-eye Atlas remained pristine. This contradiction forced scientists to reconsider assumptions about interstellar comets more broadly. Perhaps such objects are sculpted under conditions that promote internal structures, unlike anything seen in the solar system. Perhaps they grow with cleaner planes of weakness, or contain materials that fracture smoothly under thermal or mechanical stress. Or perhaps they harbour pockets of exotic ices substances rare or absent locally, that sublime into gases so transparent or short-lived that they leave no visible trail. Whatever the reason, the event pushed comet science into a space of discomfort. It hinted that the frameworks built from centuries of solar system observations might not apply universally. The universe, vast and varied, may produce bodies whose behaviour challenges the boundaries of familiar physics. The scientific community responded with equal measures of amazement and caution. Some researchers saw parallels with One-Eye Oumuamua's anomalous behaviour, noting that both interstellar visitors had evaded traditional explanations. Others urged restraint, emphasizing that without more detailed observations, conclusions remained premature. But even these cautious voices acknowledged the peculiarity. A fragmentation without debris is not merely rare, it is nearly unthinkable. The absence of dust trails meant that astronomers could not use typical diagnostic tools to reconstruct the breakup. Dust composition could not be measured. Grain size distributions could not be inferred. Jet directionality could not be traced. Even the timing of the split remained uncertain, inferred only from the gradual divergence of the fragments' paths. The event therefore existed as a ghostly imprint in the data, a mathematical artifact of motion, unaccompanied by the physical evidence normally essential to such conclusions. It was as though the comet had attempted to conceal the very moment of its own unmaking. The moment of realization, then, was not a celebration of discovery, but a quiet confrontation with impossibility. Scientists found themselves staring at two fragments, where only one should have been separated in a manner that defied every known mechanism. Observatories confirmed the findings, independently establishing the fact beyond doubt. But the deeper truth remained elusive. The universe had permitted a form of shattering whose subtlety mocked the limits of current understanding. This was not simply unexpected. It was paradigm-breaking. It challenged the assumption that all cometary breakups must conform to observable signatures. It forced researchers to imagine new mechanisms, silent ones, precise ones, ones that walk the boundary between physics and absence. In this tension between the expected violence of fragmentation and the serene emptiness observed lay the core of the mystery. 3i Atlas had defied the script written by dust and rupture. It had offered a new and unsettling possibility that in the vast dark between stars, objects may fracture in ways earthbound science has yet to imagine. The shock of this realization rippled outward, setting the stage for an investigation that would probe deeper into the heart of what interstellar matter might truly be. The laws that govern the breakup of comets are not vague suggestions, they are anchored in centuries of observation in thermodynamic principles, in the ways fragile celestial bodies respond to stress. These rules, forged through long familiarity with the solar system's icy wanderers, describe a universe where brittle structures do not fail quietly. When sunlight heats a comet's surface, temperature gradients carve cracks. Sublimating gases tear through fissures and jet outward. Rotation amplifies strain until the body can no longer hold itself together. Tidal forces rip apart objects that stray too close to massive bodies. And in every scenario, fragmentation leaves fingerprints. Dust particles outflow debris. 3i Atlas obeyed none of these patterns. It behaved as though the known rules were mere guidelines, optional, dispensable. From the moment its split was inferred, scientists were forced to confront a troubling truth. The event contradicted the very physics expected to describe it. What troubled researchers most was the comet's calm surface behaviour prior to the inferred breakup. Comets on inbound trajectories often display asymmetrical activity jets on one side, flickering brightness on another, oscillations driven by irregular heating. These signatures speak of instability, the precursors of disintegration. But 3i Atlas exhibited remarkable uniformity. Its coma expanded smoothly, its brightening curve evolved predictably. There were no surges of activity, no abrupt gas ejections, no signs of internal turmoil. Thermal stress, this simplest and most common cause of cometary breakup, seemed inconsistent with such smoothness. For a comet to fracture under heat, it must endure temperature differentials that propagate cracks through its interior. These cracks produce dust long before they break the body. Grain by grain, particles escape into the coma, forming halos visible even from vast distances. But in every frame captured prior to the fragmentation, the object's coma remained thin, muted, almost restrained. It was as though thermal stresses, if they were present, had no outward expression. Rotational breakup offered another avenue of explanation. A spinning comet can accelerate gradually until centrifugal forces exceed the cohesive strength of its structure. Yet rotational failure is messy. It casts fragments outward with measurable force, it produces dust fans aligned with the rotational axis, and it often causes sudden brightening as exposed ices rapidly sublime. None of these signatures appeared for 3I Atlas. Its fragmentation showed a kind of precision that resembled mechanical separation more than catastrophic failure. Tidal disruption represented another possibility, but here again the physics resisted. Tidal forces strong enough to tear a comet apart require dramatic encounters with massive bodies, close passes by planets, or within the inner gravitational grasp of the Sun. 3I Atlas experienced neither. Its orbit did not bring it into any dangerous proximity zone. No planetary influence approached the threshold needed for disruption. The comet simply continued its inbound path with calm inevitability, drifting deeper into sunlight but encountering nothing capable of pulling it apart. If not tides, then perhaps internal pressure from volatile ices might have ruptured the nucleus. Interstellar comets could theoretically contain exotic compounds, supervolatile materials accumulated in the distant cold, which upon heating could explosively expand and split the object. But this too would leave unmistakable residue gas emissions, spiking dust being released, shock signatures spreading outward. Instead, the coma remained weak and unperturbed. The more scientists probed, the clearer the contradiction became the comet's behaviour, before, during and after the split violated the frameworks built to explain all known fragmentation events. This was not simply odd, it was destabilizing. It suggested that the physical assumptions underlying cometary cohesion, how their internal structures hold together, and how they fail may not apply to bodies formed beyond the solar system. This realization cast a long shadow across the investigation. For decades, astronomers have relied on models based on solar system comets, which tend to be fragile aggregates of dust and ice. But 3 Atlas appeared to possess a different architecture, one that allowed it to fracture cleanly without the typical shedding of debris. This implied greater internal coherence, a strength unexpected in such ancient porous objects. It was as if the comet had been carved along a pre-existing seam, a structural plane of weakness that required little energy to separate. Such a plane could exist in theory-layered accretion. During its formation, a primordial fracture sealed by eons of cold, or a differentiation boundary created by slow thermal evolution near a distant star. But even this scenario demands that the separation produce detectable dust as the edges tear apart. The total absence of that dust suggested something even stranger. Either the material along the fracture plane was extraordinarily uniform, allowing a near frictionless separation, or the comet possessed physical properties that prevented particulate release. This second possibility verged on the extraordinary. For a body composed of brittle ices and loosely bound grains to break apart without shedding fragments, its internal matrix would need to behave in ways unfamiliar to terrestrial intuition. Perhaps it contained sintered layers regions where atoms or molecules had fused under pressure into a denser, more cohesive sheet. Perhaps cosmic rays acting over millions of years had altered its chemical landscape, strengthening some regions while weakening others. Or perhaps its internal voids had collapsed silently, absorbing the shock of separation without ejecting material outward. Each hypothesis pushed the boundaries of existing models. Each revealed how little humanity truly knows about the geology of interstellar bodies. And each forced scientists to consider the uncomfortable possibility that the solar system's comets shaped in a particular environment under a particular star may represent only one narrow branch of cometary evolution. The rules that govern solar system comets may not be the rules of the galaxy. For researchers, this realization was both thrilling and unnerving. It challenged assumptions long held as universal. The idea that fragmentation must produce dust that break up, requires violent processes, that cometary structure is inherently fragile, these principles were no longer certainties. The behavior of 3I Atlas suggested the existence of a different class of objects, comets, built with properties shaped by distant stars, foreign nebulae, or cold molecular clouds with distinct thermodynamic conditions. The shock reverberated through the scientific community. Papers began circulating proposing mechanisms that would allow a comet to split without visible evidence. Some invoked deeply buried volatile reservoirs capable of venting invisibly. Others considered materials with sublimation properties so unusual that traditional dust trails would not form. Still others proposed mechanical failure modes mediated by internal grain bonding, absent in local comets. But in each of these theories lay an unspoken recognition the rules were bending. 3i Atlas had not behaved as comets are expected to behave. It had broken the script. In doing so, it exposed something deeper a fissure not in its icy body, but in the assumptions guiding cometary science. The more researchers sought to reconcile the event with known principles, the more tension they uncovered. The phenomenon stood at the intersection of the familiar and the unknown, a quiet rebellion against the models that once seemed comprehensive. The strangeness of the fragmentation, the absence of debris, the serene behaviour of the fragments afterward, these elements combined into a single undeniable truth. 3i Atlas had violated expectations so profoundly that new frameworks were required to explain it. The mystery had deepened, and what lay ahead was an investigation that would plunge into the heart of the comet's internal secrets, guided by tools and telescopes seeking answers hidden behind the quiet perfection of its impossible split. The deeper astronomers looked, the more the void between the fragments of 3i Atlas seemed to expand, less a physical separation and more an intellectual one, stretching between what should have been visible and what the instruments insistently reported. In the aftermath of a comet's breakup, the region between fragments usually becomes a stage for spectral complexity. Dust particles shimmer under sunlight, gas molecules fluoresce in ultraviolet wavelengths, and faint threads of debris trace delicate arcs through space. But here the centre of the scene remained bare. When high-resolution imaging campaigns began, the expectation was straightforward. Telescopes equipped with sensitive detectors, including those capable of reaching just above background noise levels, were trained on the interstitial region. They searched not merely for large fragments, but for any hint of particulate matter, fine dust grains, micro-ice crystals, or even sub-micron particles. Such material, though faint, should scatter sunlight enough to form a detectable halo between and behind the separating bodies. But what appeared instead was a kind of immaculate darkness. The images revealed a clean divide, a line of separation so unadorned that it looked artificial, an absence edged sharply by two pale, drifting embers. This absence was not simply a failure of detection. It was a pattern repeated across instruments, wavelengths, and nights. Optical observatories saw nothing. Infrared surveys detected no thermal signature from residual dust. Even polarization studies, which can reveal the orientation and distribution of tiny grains invisible in direct imaging, reported no anomaly. The empty wake was not an artifact. It was real. Astronomers then examined photometric evolution. If the fragments had shed material even briefly, their collective brightness should have flickered or deviated from the predictable curve of sublimation-driven activity. Instead, light curves from each piece remained astonishingly smooth, too smooth. This steadiness suggested that the breakup occurred without exposing significant new surfaces, or that any newly exposed ice did not react violently with solar radiation as expected. Some researchers speculated that the debris might have dispersed so quickly, or been so fine that it escaped detection. They imagined particles vaporizing into gases too faint to register, or dust scattering into densities indistinguishable from the solar background. Yet even these scenarios fell short. If the comet had lost mass, that loss should have manifested somewhere in thermal signatures, in changes to coma density, or in alterations to the shape of the comet's tail. But the coma surrounding each fragment evolved with surprising restraint, maintaining a subdued profile inconsistent with any known form of fragmentation. As astronomers worked, the fragments continued to move, separating gradually, their divergence measured with increasing precision. Their trajectories did not carry the chaotic scars of recent violence. Instead, they drifted apart with a smoothness reminiscent of binary components long accustomed to shared motion. The lack of turbulent dispersal suggested that minimal force had acted during the split. Whatever had occurred inside the nucleus, it must have unfolded in a manner that exerted only the slightest of impulses. More data arrived from spectroscopic surveys. These instruments measure the distribution of gas molecules by breaking down light into its constituent wavelengths. If sublimation had increased, following the breakup, the spectral lines corresponding to major volatiles, cyanide water vapor carbon-based molecules, would have intensified. But the lines remained unchanged, presenting the same calm chemistry as before the split. The data almost implied that the breakup was chemically silent. One by one, typical signatures of cometary destruction fell away. no asymmetrical outgassing which often marks ruptures, no fluctuating jets that betray new fissures, no broadening tail caused by released debris. The comet behaved like a body that had simply decided to become two. A pattern with no precedent began to emerge. The fragments exhibited orbital behavior that, while slightly divergent, was unusually stable. Their separation velocity appeared modest, far lower than expected for any disruption driven by internal pressure or rotational stress. Rather than launching violently apart, they drifted with the gentleness of objects nudged by forces so subtle that they almost seemed choreographed. Such stability is extraordinarily uncommon. In typical breakups, fragments depart with erratic motion. They tumble, shed more material, and interact with the outflowing gas, resulting in unpredictable curves. But the two pieces of 3I Atlas followed smooth, almost parallel paths. Their relative motion suggested a shared internal structure that had divided along a symmetrical plane, as though they had been two halves of a larger whole waiting quietly for the moment to separate. This idea that the nucleus harboured a natural plane of splitting intrigued researchers. It could explain the smoothness of the event. But even in the most theoretical scenario, such a plane would be imperfect. Microscopic material should have flaked away. Dust grains should have scattered. Heat should have vaporized exposed ices. The immaculate emptiness therefore persisted as an impossibility. More intriguingly, the stability of the fragment motion hinted at internal density uniformity. Comets typically contain heterogeneous mixtures, pockets of dust veins of ice regions of varying strength. These inconsistencies cause fragments to recoil with uneven forces. But the clean post-breakup motion of 3I Atlas implied a degree of homogeneity almost unheard of in cometary science. Its internal structure might have been layered with an elegance seen only in laboratory analogues, not in natural objects forged in turbulent protoplanetary environments. And with every new measurement, the mystery deepened. If the comet was uniform enough to split cleanly, stable enough to drift without tumbling, and quiet enough to shed no detectable debris, then it must belong to a category of objects not previously documented. Perhaps its interstellar origin played a role. Exposure to cosmic radiation over millions of years might have altered its material's sintering grains into an unexpectedly cohesive matrix. Or the environment of its birth, a cold molecular cloud or a distant star system with different chemical ratios, may have produced ices capable of fracturing without releasing dust. Whatever the answer, the empirical void in the wake of 3I Atlas became a kind of signature in itself. It forced scientists to pay attention not to what was present, but to what was absent. In the silent gap between the fragments, the universe had drawn a line that resisted interpretation, a clean divide carved not by visible forces but by the invisible precision of a process that defied all precedent. Where dust should have drifted, there was darkness. Where chaos should have reigned, there was symmetry. The wake of the breakup had become the most eloquent part of the comet's story, a void that whispered of structural mysteries buried deep within the interstellar night. As the fragments drifted farther apart, their motion settled into a rhythm that troubled even the most conservative analysts. For all the emptiness that lay between them, the two pieces of 3I Atlas behaved with a kind of measured coherence, as though responding to a script written long before they entered the solar system. The kinematic pattern they traced was unlike anything recorded for a disrupted comet. Instead of erratic deflections or sudden divergences characteristic of bodies torn apart by internal stress, they moved with the grace of objects separating along an invisible seam, smooth, deliberate, and eerily stable. This stability became the first defining feature of the pattern with no precedent. In typical cometary breakups, fragments inherit rotational complexities from the parent body, irregular torques, asymmetric outgassing, or imbalanced mass distribution. These factors imprint chaotic signatures onto their motion, but 3I Atlas's fragments exhibited none of this. They drifted with minimal differential rotation, almost as if their angular momentum had been partitioned equitably between them. Such balance is rare in natural breakups and practically unheard of in one so silent. The orbital evolution made the anomaly even clearer. The fragment separation velocity, the speed at which they drifted from one another, was exceptionally low. Cometary disruptions often produce higher ejection velocities because the forces that tear the nucleus apart act abruptly, pushing pieces outward with measurable impulse. But here the speed was not merely small, it was elegant in its smallness. It resembled the slow divergence of components that had been barely held together, or perhaps held together too perfectly, until the most minute internal shift encouraged a silent parting. Further observations refined the orbital solutions. When researchers plotted the motion of the fragments across days and weeks, they saw signs of extraordinary dynamical consistency. Their trajectories suggested that the breakup had been nearly symmetrical, with minimal lateral forces acting at the moment of separation. Instead of abrupt thrusts or chaotic recoil, the data indicated a near-precise division, like two petals drifting apart after the loosest release of pressure. This led some scientists to consider whether the comet harboured a crystalline internal structure. While no natural comet in the solar system has displayed such architecture, interstellar environments may produce conditions in which ice is deposited in patterned layers forming a lattice-like interior. Over millions of years, cosmic rays can catalyze slow rearrangements of crystalline bonds, strengthening certain regions while weakening others. If 3I Atlas possessed such ordered layers, its breakup could have occurred along a boundary where the lattice had become unstable, yielding a parting that required little force and generated almost no debris. Spectroscopic measurements lent subtle support to this possibility. The spectral fingerprints of the fragments showed consistency across both pieces. Their volatile composition matched remarkably, suggesting that each half represented an almost perfect mirror of the other. Comets formed in the solar system often display compositional gradients, one region harbouring pockets of dust, another rich in certain ices, another containing darker materials. But here the similarity in spectral behaviour implied an even distribution of volatiles, reinforcing the notion that 3I Atlas may have been carved by processes more uniform than any known to local cometary science. The deeper scientists probed these patterns, the more the mystery seemed embedded not only in the breakup itself, but in the very nature of the comet's internal geometry. If the object's interior featured a plane of weakness that aligned perfectly with its structural symmetry, this could explain why the fragment's shapes, though still unresolved, appeared to produce similar light curves. Observers noted that the brightness evolution of each fragment tracked closely, as though their exposed surfaces responded in tandem to solar heating. Again, this level of uniformity had no clear analogue in known comets, whose irregularities produce much more complex brightness patterns. The pattern with no precedent extended further into the behaviour of the coma. After fragmentation, one expects the coma to reshape itself, expanding unevenly as new active regions emerge. Yet the coma around each fragment evolved gently, its profile remaining narrow and faint. Researchers were particularly struck by the absence of halo expansion, or transient jets from the newly exposed surfaces. Instead, each fragment seemed to maintain a controlled rate of sublimation, another indicator that the breakup had not been violent enough to disturb the brain-like networks of microchannels normally responsible for gas release. This led some theorists to consider whether 3I Atlas had fractured in a quasi-static manner. Instead of a sudden rupture triggered by explosive sublimation or mechanical failure, the breakup may have occurred gradually, the internal structure relaxing along a plane until the binding strength quietly fell below the threshold required to maintain unity. In this model, the nucleus would surrender to its own symmetry, with the split occurring almost as a geological creeping event, slow, near frictionless, and devoid of dust. Such behaviour has no analogue in solar system comets. But in the interstellar medium, where objects experience deep cold cosmic radiation exposure and potential interactions with molecular cloud chemistry, the evolution of their interiors could differ dramatically. The slow build-up of stresses, the annealing of certain materials, or the subtle redistribution of volatiles might all contribute to a behaviour that defies the abruptness familiar to terrestrial comet observations. As the fragments travelled onward, astronomers charted deviations in their motion with exquisite sensitivity. In these measurements lay a final tantalizing clue. The tiny differences in trajectory suggested that each fragment carried slightly different mass distributions, but not enough to indicate chaotic separation. Instead, the divergences resembled what might occur if a single cohesive nucleus had split into two nearly equal halves, each retaining enough structural integrity to move independently without disintegrating further. This soft divergence cemented the unprecedented nature of the event. The cosmos had revealed an object whose fragmentation was not driven by violence, but by an internal choreography guided by properties unseen in local cometary populations. A comet that obeyed patterns not recorded before. a pattern that spoke of origins distant, of materials unfamiliar, of formation histories beyond the reach of current models. The behaviour of 3I Atlas was not merely unusual, it was a message written in motion, a geometry of separation that hinted at the deeper nature of interstellar matter. With every hour of drift, the fragments traced a story that no known comet had ever told, urging scientists to look beyond the familiar physics of rupture and into the possibility that the galaxy harbours bodies shaped by rules not yet imagined. As astronomers pieced together the story of 3I Atlas's breakup, one discrepancy loomed over every attempt at explanation. The comet had clearly lost mass, and yet none of that missing material appeared anywhere in the data. The fragments were smaller than the original nucleus. Photometric analysis translating brightness into approximate surface area revealed a measurable shortfall between what the comet had been and what it had become. This deficit could not be dismissed as observational error. It was real, a subtraction written directly into the light curves. Something had vanished. But where had it gone? In the familiar script of cometary fragmentation, missing mass almost always reveals itself as dust. Not always large grains, often the opposite. The majority of material shed during a breakup exists as fine particles drifting in the comet's wake, scattering sunlight into delicate spectral textures that even modest telescopes can detect. Dust clouds linger. They glow faintly. They leave trails. They speak. Yet 3I Atlas left no such record. Its wake remained as silent and clean as an untouched field of snow, unmarked by any motion. No brightening of the coma, no enhancement in scattered light, no thermal glow from heated dust, no polarization signature, nothing. This absence forced scientists to re-examine the breakup with new suspicion. If the comet had lost mass but produced no observable debris, then the missing material must have escaped in a form that left no trace detectable through the normal channels of observation. Several possibilities emerged, but none aligned easily with known physics. One of the earliest theories proposed that the lost mass vaporized immediately into gas too sparse to be detected. But such vaporization would require an extraordinary heat input. Interstellar comets hardened by eons of deep cold do not respond to sunlight with instantaneous sublimation at that scale. The energy required to convert that much solid material directly into gas without leaving transitional phases, micro-ice crystals mixed, particulate grains, would be immense, and the products of such vaporization would still appear in spectroscopy as temporary enhancements in volatile signatures. But spectrometers sensitive to even faint injections of cyanides, water vapor and carbon compounds detected no spike. Another suggestion was that the missing mass dispersed into particles so small, nanometer-scale grains or even molecular clusters, that they became effectively invisible. Such ultrafine dust behaves like gas, merging indistinguishably with the solar wind. Yet even here, instruments capable of detecting scattered sunlight should have observed a softening of the background profile. They did not. The space around the fragments remained pristinely smooth. This led some researchers to consider a radical scenario: the missing mass might have been trapped within the comet's interior, until the moment of separation, then released into a vacuum, not as debris but as a coherent plume of gas, so cold and brief that it dissolved into space within moments. In such a model, a pressure reservoir within the nucleus could have ruptured during the breakup venting stored volatiles in a short silent exhalation. But this hypothesis struggled against thermodynamic constraints. Internal reservoirs large enough to store significant mass would leave thermal signatures or structural distortions observable before the split. 3I Atlas showed none. The weight of the missing mass pressed harder on every model. If the fragments were cleanly split halves, the deficit could be small. But if the original nucleus had been irregular, elongated, asymmetric, the mass loss could be significant. Without a resolved shape, astronomers were forced to estimate from brightness alone. But even conservative estimates implied that more than a negligible portion of the comet had vanished. And so the riddle became sharper. A body of ancient ice entered the solar system, it warmed gently, it split, and a measurable fraction of its substance simply disappeared. Some researchers began exploring mechanical explanations that skirted the boundaries of known comet physics. Perhaps the breakup coincided with internal collapse, with material falling inward rather than outward. In such a scenario, a cavern or void inside the nucleus might have compressed during the separation, swallowing loose material. Collapses are known in terrestrial ice structures and even in some solar system comets, but those events still produce external debris, Nothing collapses perfectly. Nothing seals itself so wholly that not a grain escapes. Yet 3i Atlas behaved as though such perfection were possible. Others turned to the prospect of exotic icy substances rare or unstable in the solar system, but potentially common in other star systems. Certain volatile compounds such as supercooled nitrogen or carbon monoxide ices can undergo rapid phase transitions that produce very little dust. If a significant portion of the comet were made of such materials, the missing mass might have vaporized cleanly. But again, spectroscopy betrayed no hints of these exotic volatiles. Their presence should have left faint lines, ephemeral though they might be. The lines were absent. The possibility remained unsettling in its implications that the missing mass constituted a type of material that does not interact with light, as normal particulate matter does materials that scatter poorly, sublimate quietly, or dissipate with an efficiency unknown in solar system environments. This did not demand exotic physics, merely unfamiliar chemistry. Interstellar objects form in environments shaped by different pressures, different radiation fields, different histories. They may accrete grains with unusual optical properties. They may incorporate compounds altered by long exposure to high-energy cosmic rays. They may hold structures whose behavior upon heating diverges from local intuition. The more the missing mass was studied, the more it appeared to reflect not a flaw in the data, but a flaw in the assumptions guiding the interpretation of the data. There was also the possibility of a process even stranger, that the breakup had occurred long before it became visible, and that by the time astronomers detected the divergence of the fragments, the missing mass had already dispersed beyond measurable density. If the separation happened farther from the Sun under colder conditions, the particles released could have travelled great distances before sublimating or blending invisibly into the interplanetary medium. In this scenario, the observed split was merely the end of a long unfolding separation, but even this theory clashed with observations. Earlier imaging showed no elongation, no hints of doubling, no transitional stages. The transition from unity to division occurred too quickly to support a long-delayed separation. What remained was a kind of scientific discomfort, an acknowledgement that a portion of the comet's substance had vanished in a manner inconsistent with established models. The missing mass became a symbol, a quiet reminder of how little is known about interstellar geology, a reflection of cosmic processes that occur far from Earth shaped by forces humanity has not yet mapped. The weight of this absence did more than perplex astronomers. It set the stage for speculation that would probe the boundaries of comet physics, forcing researchers to question whether the materials forged in distant regions of the galaxy obey the same rules as those formed close to home. If the mass had not escaped violently, nor lingered visibly, nor left signatures in the surrounding space, then perhaps the very nature of the material itself was the key. Perhaps the galaxy harbours substances that fracture without leaving a trace, substances that behave like whispering ghosts fading into silence even as they depart. The fragments of 3i Atlas continued their paths, silent witnesses to the loss. Their motion carried the unspoken implication part of the comet had slipped away into the vastness, leaving behind only a void in the data, an absence that demanded explanation, yet resisted every attempt to provide one. Spectroscopy became the next instrument of revelation, not because it exposed the mechanism of the breakup directly, but because it revealed the tapestry of the comet's chemistry with a subtlety no other tool could match. If 3i Atlas had concealed its fragmentation behind silence, then perhaps its composition would whisper clues about the kind of material capable of breaking without producing debris. For months, teams across the globe gathered spectra from both fragments, examining every wavelength for hints of what this object was made of, how it formed and why it behaved as it did. At first glance, the spectral signatures appeared broadly familiar. The comet exhibited emissions from volatile compounds commonly found in solar system comets, faint cyanide bands, traces of carbon-bearing molecules, and the characteristic fingerprints of water ice sublimating into vapour. This was expected. Interstellar comets, though born of distant stars, still arise from protoplanetary disks, where the fundamental chemistry of ice and dust resembles that of our own. Yet beneath this familiarity lay subtler patterns, anomalies, asymmetries and absences that resisted easy categorization. One of the earliest clues came from the relative weakness of water emission lines. Comets entering the inner solar system typically bloom in water vapour as they warm, releasing plumes that dominate their spectra. But 3i Atlas produced surprisingly little water vapour relative to its total brightness, suggesting that water ice was either less abundant or less accessible. Instead, carbon monoxide and carbon dioxide, the deeper frozen volatiles, played a more prominent role. Their elevated ratios hinted at a body forged in an environment colder than any region where solar system comets originate, perhaps near the shadowed edges of a protoplanetary disk or within a molecular cloud more ancient than our Sun. Such chemistry matters. A comet rich in supervolatiles formed at extremely low temperatures may possess internal structures unlike any known comet. Supervolatiles can migrate slowly through porous materials, even at far distances, reshaping the interior over millions of years. They can create layers of hardened deposits, pockets of pressurized gas, and crystalline structures that behave unpredictably under thermal stress. If the nucleus of 3I Atlas contained such layers, its breakup could have followed pathways unfamiliar to standard comet models, fracturing along planes defined not by mechanical weakness alone, but by chemical evolution frozen into its architecture. Another clue emerged from the relative absence of dust-related spectral features. Comets that shed particles reveal them not only through scattered light, but through absorption and emission lines associated with silicates and organics. 3I Atlas showed fewer such features than expected. The dust signature was remarkably faint, so faint in fact that some researchers began questioning whether the comet had a lower than normal dust-to-ice ratio. Dust-poor comets exist, but they are uncommon. If this interstellar visitor were composed predominantly of ices with very little embedded dust, it could explain the lack of particulate material during fragmentation. A dust-poor body could break apart along icy plains that produce gas but little solid debris, but the faintness of dust features did not necessarily imply dust absence. Another possibility was that the dust grains were unusually large or unusually small. Large grains, millimeter scale or larger, scatter light poorly and may behave more like compact chunks falling behind in detectable ways only under strong solar radiation. Extremely small grains, nanometer scale clusters interact differently with sunlight slipping into the background of space, without leaving the characteristic spectral signatures typical of cometary dust. If 3I Atlas's dust distribution skewed towards such extremes, its breakup could produce almost invisible particulate dispersal. Researchers turned to polarization spectroscopy for help. Polarization studies can reveal the shape alignment and size distribution of dust particles even when they cannot be imaged directly. To their surprise, the polarization patterns were weak, much weaker than those of typical comets. This again hinted at either a scarcity of dust or dust grains with optical properties not commonly seen in solar system bodies. The possibility grew more enticing. Interstellar radiation, especially cosmic rays, may have processed the comet's grains in ways that altered their surfaces, making them more transparent, less reflective, or more irregular in shape. Another peculiar detail surfaced in the infrared range. Thermal emissions from the coma were lower than expected, even accounting for the comet's modest brightness. This suggested that the grains present, if present at all, were not absorbing and re-radiating heat efficiently. Some researchers speculated about the presence of amorphous ices or porous aggregates with extremely high void fractions. Such materials can fracture cleanly, sublimating into gas without producing fine dust. In laboratory analogues, porous ice matrices collapse silently, leaving minimal residue, an eerie echo of what astronomers observed in 3I Atlas. The chemistry also revealed hints of organic compounds, complex carbon chains, and fragments of prebiotic molecules. These are common in comets, but their ratios relative to the overall volatile content were unusually high in 3I Atlas. These organics may have filled the interstitial spaces within the comet's structure, acting as brittle binders or stiffening agents. If the interior contained aromatic organics or radiation-hardened carbon networks, the breakup dynamics could differ drastically from the behavior of typical comets, which are held together largely by weak van der Waals forces between dust and ice. The composition therefore painted a portrait of contradiction, a comet chemically similar to typical icy wanderers, yet behaving physically as if governed by entirely different principles. One hypothesis grew increasingly compelling among researchers, that the comet had formed in an environment with a very different balance of temperature radiation and pressure conditions capable of producing ices with unique mechanical properties. For example, layered crystalline structures alternating with deposits of supervolatile compounds could fracture under precise conditions without producing debris. Grain boundaries formed through ancient cosmic ray processing might act as planes of separation. And pressure pockets formed during slow thermal migration of volatiles might vent silently, contributing to a clean split that leaves no detectable signature. Spectroscopy in this sense became a quiet guide pointing toward an origin far colder, far darker, and far older than any comet in the solar system. It suggested a body shaped by the quiet chemistry of interstellar space, refined over ages by cosmic rays, sculpted by crystalline reforms and strengthened or weakened in unfamiliar ways. The chemistry whispered something else as well, that the breakup was not merely an anomaly, but a reflection of the comet's birth. Its behaviour was encoded in its composition, written into its molecular framework long before it ever reached the Sun. Every absence of dust, every understated emission line, every spectral quietness hinted that the comet was built to fracture differently, that its materials were capable of splitting in ways that mimic geological precision rather than explosive decay. In the end, spectroscopy offered not an answer, but a palette of clues. It ended the illusion that the breakup could be explained through surface behaviour alone. It redirected attention inward into the buried layers of chemical evolution. It opened the door to theories of internal transformation and silent fracture. And it deepened the mystery by revealing that the comet's composition was not simply strange, but strangely suited to the silent riddle written across the empty space between its fragments. The deeper astronomers traced the spectral breadcrumbs of 3I Atlas, the more attention shifted from what coated its surface to what might have been happening beneath it. Spectra could sketch the outer layers, but they could not reveal the hidden machinery embedded within the nucleus machinery that might have guided the breakup from inside rather than erupting outward in the familiar cometary violence. If the fragmentation had produced no debris, then perhaps the fracture was not driven by external forces at all, but by something unfolding quietly in its interior pressure crystallization phase, transitions or deep thermal rearrangements that only interstellar evolution could script. Interstellar comets are cold in a way nothing in the solar system can match. They drift for millions, perhaps billions of years, through regions where the background temperature hovers above absolute zero. In such darkness, their ices undergo processes alien to local comets. Molecules freeze into amorphous states, rearrange under cosmic ray bombardment, and form metastable structures that sit poised between rigidity and collapse. When warmed by sunlight, these ancient arrangements do not always behave predictably. They can release pressure in slow, silent exhalations, restructure in cascades invisible to spectrometers, or crack along crystalline planes with almost surgical precision. One of the most intriguing possibilities was the role of amorphous to crystalline ice transitions deep within the nucleus. Amorphous ice, unlike its crystalline counterpart, traps volatile molecules within its structure like tiny locked rooms. Over vast interstellar timescales, cosmic rays can also lodge into these chambers, building subtle internal tension. When amorphous ice warms past a critical temperature, it reorganizes suddenly into a crystalline lattice, releasing trapped gases. This transition can generate internal pressure without producing dust, because the transformation occurs within the ice itself, rather than along exposed surfaces. If such a transition occurred in 3I Atlas, not near the surface but deep inside, it could have produced a pressure gradient that gently pried the nucleus apart. In typical comets, such pressure escapes explosively venting dust and gas through cracks. But if the comet's interior were unusually porous or composed of interconnected chambers, the pressure may have distributed evenly, diluting the violence. Under this model, the nucleus would expand slightly, stretching along a natural internal weakness until the structure parted not with a blast but with a sigh. This scenario dovetailed neatly with the observed behaviour, a clean separation, two stable fragments, no evidence of particulate blowout. But even here questions lingered. Thermal models suggested that sunlight would trigger such transitions at varying depths depending on composition. Yet the timing of the breakup, inferred from fragment separation, seemed almost too precise, occurring neither too early nor too late, but exactly when the comet reached a certain thermal threshold. It was as though the interior had waited for a cue. Another possibility emerged from the physics of sublimation pressure. Deep within comets, volatile substances like carbon monoxide or nitrogen can accumulate in pockets. When warmed even slightly, these volatiles expand, creating pressure domes beneath the surface. On Earth, trapped gas creates explosive fractures, but in materials subjected to extreme cold for millions of years, Such pockets can form thin, brittle layers that hold uniform pressure until the slightest stress causes them to rupture with uncanny delicacy. If 3I Atlas contained such a dome aligned along a structural boundary, the warming from the sun could have nudged it past the tipping point. But instead of exploding outward, the internal pressure may have escaped sideways, prying the nucleus apart along a seam, while leaving its outer skin largely intact. The internal rearrangement could have been so slow and so controlled that only the final opening of the crack produced any motion, and even then gentle enough to avoid ejecting dust. Researchers also explored the possibility of thermal conductivity anomalies. Some interstellar comets may contain layers of material with radically different conductive properties, dense crusts atop fluffy interiors, crystalline strata alternating with porous deposits. Heat penetrating such a body does not propagate evenly. Instead, it can concentrate along certain paths, creating localized zones of expansion and contraction. In this view, 3I Atlas might have fractured as a result of differential expansion, one region swelling slightly while a neighboring region held firm. Over time, tension accumulates until separation occurs following the path of least resistance. If the difference in thermal expansion was small, the resulting fracture could be clean and nearly debris-free. Perhaps the most radical possibility involved exotic internal structures shaped by long exposure to cosmic radiation. Over millions of years, atomic-scale damage accumulates in interstellar ice. This slow bombardment can produce microcracks, but it can also induce bonding between grains, forming a kind of radiation-hardened matrix. Such a matrix might behave less like the powdery, loosely aggregated material of solar system comets, and more like compressed brittle glass. Under the right conditions, such glass-like structures can fracture along smooth planes, producing shards that separate cleanly rather than disintegrating into dust. If 3I Atlas had evolved such structures within its core, then its breakup might resemble geological cleavage rather than cometary destruction. The nucleus could split along a radiation-created plane like a rock, breaking along a fault line, leaving behind two smooth surfaces and no rubble. This scenario also aligned with the fragment's stable motion. Brittle materials break cleanly, imparting little rotational disturbance. The debris that does emerge from such fractures can be microscopic enough to vanish in sunlight within hours. Still, the cleanest fractures on Earth, even in highly crystalline rock, produce some debris. Why had 3I Atlas produced none detectable? This question led researchers to consider internal reabsorption processes. If the fracture occurred deep inside the nucleus dust produced by the break, might have been captured within porous cavities rather than expelled outward. In such a scenario, the fracture line might extend outward silently, while all released particulate fell into internal voids. The comet could break like a hollow shell, two halves splitting, without releasing material through the outer surface. The dust would remain inside, trapped and undetectable. This model, though elegant, required the comet to possess extensive internal caverns, geometries that, while plausible in icy bodies, are rarely so perfectly aligned with structural weaknesses. Yet given the unusual chemistry revealed in spectroscopy, researchers could not rule it out. Interstellar evolution might sculpt internal landscapes far stranger than the simple rubble piles familiar in solar system comets. Some theorists proposed even more subtle mechanisms, microphase transitions within organic-rich regions where radiation-hardened carbon networks become brittle at certain temperatures, localized sublimation fronts migrating inward rather than outward, or even delayed mechanical relaxation where stress is frozen into the nucleus during formation, finally unwind under solar illumination, allowing the structure to release tension accumulated across epochs. Across all these scenarios, one theme persisted: the fracture of 3I Atlas was not driven primarily by external forces. It was shaped from within by chemical, thermal and structural histories hidden beneath its surface, sculpted during its long journey through interstellar darkness. The comet's silent split became a mirror for the unseen forces that govern matter in the cold, deep spaces between stars. It suggested that interstellar geology may operate on principles more complex and delicate than expected, shaped less by sudden violence and more by slow internal orchestration. What the telescopes witnessed was merely the final act of a process that had been unfolding quietly for ages. A process encoded in the comet's interior, written in layers of ice pressure and crystalline history, and revealed only when sunlight warmed it enough to let the structure sigh apart. The mystery no longer resided only in what astronomers saw, but in everything they could not see. The invisible fractures, the unseen pressures, the silent rearrangements that shaped a breakup so precise it left no trail. 3i Atlas had revealed that the deepest forces in cometary physics might lie not in the star's heat or the planet's tides, but in the quiet transformations occurring in the frozen hearts of bodies that drift between them. The deeper investigators ventured into the mechanisms hidden beneath the comet's icy skin, the more one question surfaced with an unsettling clarity. If the fragments had separated cleanly quietly without debris, then what invisible force had served as the final knife? It could not have been the expected eruption of dust or the chaotic forces that normally accompany sublimation. Instead, astronomers began exploring a class of processes far more elusive events, driven not by solid matter, but by gas alone. Gas that leaves no trail. Gas that escapes too briefly to register. Gas that might cleave a nucleus with a single, nearly undetectable breath. In cometary physics, gas is usually the herald of activity. It builds comae, sculpts, tails, shapes jets. When volatiles sublimate, they drag dust along with them, stirring brightness, reshaping surfaces, and announcing thermal stress through visible signatures. But there exists a narrower and far stranger possibility: rapid gas release without dust entrainment. Sublimation can occur in modes so clean, so fine, and so fleeting that it expels no particulate matter at all. These events are rarely seen, for they require precise internal conditions that might be common in the deep freeze of interstellar space, but nearly impossible within the solar system. Could 3i Atlas have been torn apart by such invisible winds? To answer this, scientists examined the physics of sublimation fronts, the boundaries within a comet where temperature and pressure catalyze the transition of ice into vapor. In typical comets, these fronts migrate outward as sunlight warms the surface. But in bodies with unusual thermal properties, the front can also move inward, penetrating deeper layers that had remained dormant for millions of years. When such fronts meet pockets of super-volatile material carbon monoxide, nitrogen, methane, they can trigger sudden localized gas releases. Imagine a sealed chamber within the nucleus filled with volatile gas accumulated over epochs. As internal ice transitions, the chamber's boundary weakens. A minuscule crack forms. Gas escapes in a rush so rapid that it produces a directional force weak in absolute terms, but decisive when acting on a fragile structure already under stress. If such an event occurs along a pre-existing internal weakness, the force can pry the nucleus open, like a book generating a split without scattering dust because the molecules involved are too light to entrain solid particles. Such gas jets are theoretically capable of imparting the sort of gentle separation velocity observed in 3i Atlas. They can nudge fragments apart without sending them tumbling. But these invisible winds would need to be both powerful enough to drive a structural failure and clean enough not to disturb the surrounding coma. To explore this, researchers ran models simulating how gas jets behave inside porous bodies. The simulations revealed an intriguing result if the porosity and grain size distribution were extraordinarily uniform. As the comet's prior stability suggested, then gas could travel through internal channels without generating surface eruptions. The gas would seep inward, find a weak plane accumulate along it, and ultimately push outward with distributed force. The breakup in this case becomes less an explosion and more a separation, mediated by uniform internal pressure, a controlled release across a well-defined boundary. From the outside, such a process would be almost invisible. Gas escaping from within the fracture could diffuse too quickly to leave a signature. It might disperse before entering the coma. It might vanish into vacuum before telescopes, even sensitive ones, had a chance to detect it. But some scientists proposed an even more tantalizing mechanism: coherent outgassing. In this scenario, a sheet of gas emerges along an entire plane simultaneously, rather than through a single crack or vent. Such an event requires a unique alignment of factors: uniform thermal penetration, evenly distributed volatiles, and a structural boundary ready to give way. If all these elements converge, the result would be a curtain-like release of gas, a sweeping breath passing through the nucleus with extraordinary uniformity. This gas sheet would apply equal force across a large surface, splitting the comet without disturbing the exterior shell significantly. Coherent outgassing is rare in theory and unobserved in practice. But for an interstellar object with a highly homogeneous interior, something the spectral and dynamical clues hinted at, it may be more than mere speculation. Cosmic rays, for example, could restructure internal materials into unexpected patterns. Interstellar chemistry could produce layers of supervolatile compounds stacked with geological precision. If the structure held such hidden symmetries, a symmetric release of gas becomes more plausible. Still, the clean separation left an important question, unresolved if invisible winds had played the role of the knife. Why had no trace of the gas lingered? The answer may lie in the speed of dispersal. Molecules like CO and N2 are capable of escaping into vacuum at velocities that exceed cometary escape speeds by enormous factors. When released suddenly, they radiate outward so quickly that their density plummets within seconds. In the sunlit environment of the inner solar system, these gases can ionize or dissociate almost instantly. The signature they leave is fleeting, narrow, and often too diffuse to register, beyond the noise floor of large surveys. Some researchers suggested that the gas release might have occurred during a period of observational gap, sometime between scheduled surveys when telescopes were not pointed at the comet. In this case, even a detectable event could have gone unnoticed, its molecular traces fading long before instruments returned to the scene. But even this explanation leaves a residue of doubt. For the fragmentation to be as gentle and symmetrical as observed, the gas release must have been exquisitely balanced. Too strong and the fragments would have raced apart. Too weak and no separation would occur. The event had to act like a surgeon's blade, clean, precise, and strangely considerate of the structure it divided. This led to a deeper, more unsettling thought. Perhaps the breakup was not driven by a single wind, but by a synergy of gas flows and internal restructuring. That is, gas did not create the fracture. It exploited one already forming through crystallization, pressure shifts, or thermal differentials. In this view, the internal transformation set the stage and the gas merely nudged the process across the threshold. A whisper, not a shout. A breath of wind that leaves no trace. A force invisible not because it lacked power, but because it acted along a fault line sculpted by millions of years of interstellar evolution. In the end, the idea of winds that leave no trace expanded the horizon of cometary physics. It showed that a nucleus might be shaped not only by dust and ice, but by internal flows too fine to see too precise, to measure flows capable of rewriting the rules of fragmentation. 3I Atlas, in its silent division, revealed the potential for processes that act from within, hidden from sunlight and unmarked by debris, carving a boundary between two worlds with nothing but pressure phase shifts and the lightest of escaping breaths. As the invisible winds hypothesis settled uneasily into the growing catalogue of explanations, another question rose to prominence, one that carried its own quiet gravity. If neither dust nor violent jets nor catastrophic pressure surges had torn the comet apart, then could the cause have come from outside? Could 3I Atlas have been split by forces so gentle, so subtle, that they left no trace in the data except the separation itself? Gravity, after all, requires no debris. It exerts no visible hand. It needs no plume or fracture signature. It can tear structures apart silently, not through impact or collision, but through differential pull, through the quiet reshaping of motion. Yet the known sources of tidal disruption in the solar system were easily ruled out. The comet's trajectory brought it nowhere near a planet. It never skimmed close enough to the sun to feel more than the mildest gradient of gravitational strain. Nothing in its immediate environment appeared capable of exerting the kind of force needed to break a cohesive nucleus, and yet the fragments' separation velocity, their smooth divergence and the symmetry of motion hinted at a breakup driven less by internal violence and more by a force of steady directional pressure. So astronomers turned their attention to other gravitational influences, ones weaker, stranger, or more complex than those encountered in conventional cometary dynamics. One of the first possibilities explored was non-tidal gravitational interaction with unseen mass. The solar system is filled with microstructures, dust streams, pebble clusters, gravitational gradients left behind by long-dissolved comets. But none of these could account for the symmetry of the split. The fragments showed no sign of collision deflection or sudden torque. Their paths after the breakup were smooth, not jittered or perturbed. Whatever separated them did so evenly. Next came the idea of gravitational focusing small accelerations caused by passing through regions of uneven mass distribution. In theory, if the comet had drifted into a faint but coherent tidal gradient created by some extended structure, a thin current of matter in the interplanetary medium, or a region shaped by the wake of an ancient large comet, the nucleus could have experienced unequal pull across its length. If the gradient were incredibly subtle, its effect might accumulate over time, stressing the interior until a silent fracture occurred. This model carried some beauty. It explained the gentle motion, the lack of debris, and the symmetrical behavior of the fragments. But it also required a structure invisible to all modern instruments, a mass distribution so faint and extended that it leaves no mark except on the weakest, loosest bodies. No such structure is known. No indirect evidence hints at it. And while interstellar space contains filaments of molecular gas and dust, the solar system's interior is too sparse for such gradients to accumulate meaningfully. Another possibility emerged from the larger-scale dynamics of the comet's interstellar path. Before entering the solar system, 3I Atlas travelled for unknown epochs through regions where gravitational interaction with passing stars, molecular clouds, or other interstellar objects could have strained its structure. Tidal forces in stellar encounters can stretch bodies, gradually imprinting stresses frozen into their interiors. These stresses may persist for millions of years, waiting only for a small nudge like mild solar heating to complete the fracture. In this scenario, the Sun played no active role. It merely finished a breakup that had begun long ago when the comet passed near a distant star and experienced a differential pull strong enough to prime a structural plane within it. Over time, the interior may have relaxed and shifted, but not fully healed. When the Sun's warmth softened the ice just enough, the ancient stress line reopened. This would explain the cleanliness of the break. The structural weakness was old, crisp, and deeply embedded. No debris would have been produced at the moment of separation, because the stress fracture was already present, held together weakly by frozen materials that quietly surrendered as internal temperatures rose. This model resonated with theories of deep interstellar processing where comets become libraries of ancient stress, storing the fingerprints of encounters across star systems. But even this elegant hypothesis fell short of explaining one crucial detail. Why did the two fragments separate with such measured gentleness? A stress fracture alone does not determine the velocity of separation. It merely initiates the split. Something else must have guided the fragments into motion. To answer this, astronomers explored a category of gravitational influence, far more subtle forces arising not from tidal pull, but from the interplay of radiation pressure and the comet's own mass distribution. Radiation pressure, the push of photons against a surface, usually affects dust grains, not kilometre-scale bodies. But if the nucleus had already been weakened along a plane, even faint differences in exposed surface area could cause one half to drift slightly away from the other. Solar radiation could in principle act like a gentle breeze nudging two leaves apart, slow, consistent, and clean. Under this model, the Sun did not split the comet. It merely helped the fragments drift once the separation began. The quietness of the breakup, the absence of debris, and the low relative velocity between fragments all align with this idea. The nucleus, already primed by ancient interstellar stresses, simply parted when warmed. Radiation pressure did the rest. But another gravitational factor lay waiting in the background. As 3I Atlas passed deeper into the solar system, it entered regions where gravitational perturbations from planets, though weak at great distance, can produce highly specific effects on fragile bodies. If the nucleus was already near failure, the slight differential force exerted by planets over time, even small fractions of a millimetre per second, could tip the balance. Jupiter, for instance, exerts gravitational influence across vast distances. While not strong enough to tear a comet apart, its persistent pull can subtly distort trajectories. If the comet's internal cohesion was already compromised, such distortions might have been enough to complete the split. This interplay between ancient tidal stress, modern gravitational perturbation, and the faint push of sunlight painted a portrait of a breakup driven not by dramatic forces but by harmonized subtleties, a graceful unbinding shaped by interactions too gentle to leave evidence except in the way the fragments drifted. The more scientists analyzed these possibilities, the clearer the conclusion became. Gravity in all its quiet forms may have played a role not as a destroyer, but as a sculptor. Not in tearing the comet violently apart, but in guiding a fracture whose origin lay deep in its past, written into the icy matrix long before it entered the solar system. In the end, the idea that gravity, gentle, persistent, and almost imperceptible, acted as the knife that split 3I Atlas, became part of the broader narrative. A narrative where forces so faint that they leave no wake and no plume can nevertheless align perfectly with a pre-existing internal weakness, carving a silent division through an object shaped by a lifetime of interstellar drift. A comet split by whispering forces, not roaring ones. A fracture written not by chaos but by quiet celestial geometry. Rotation entered the investigation not as a dramatic final suspect, but as a quiet, persistent presence, an invisible companion to the comet's drift, influencing its internal stresses without ever drawing attention to itself. For most comets in the solar system, rotational breakup is a process marked by violence. As sunlight sublimates, ices unevenly jets erupt from localized regions imparting torque. Over time, the nucleus spins faster and faster, stretching itself like a dancer pulled outward by centrifugal force. When rotation exceeds structural strength, the body rips apart, flinging pieces away in chaotic spirals. Dust erupts. Surfaces crumble, trails appear. In 3i Atlas, none of this occurred. And yet rotation in its gentlest form may be one key to understanding the comet's silent divide. To begin unravelling this contradiction, researchers revisited the light curves collected during the weeks before and after the breakup. Light curves often carry the fingerprints of rotation, periodic brightening and dimming as irregular surfaces spin in and out of view. For 3i Atlas, the signal was faint, but present an oscillation too subtle to reveal a definitive period but strong enough to suggest slow, deliberate rotation. Crucially, the rotation appeared stable. There was no evidence of rapid acceleration, no erratic shifts, no chaotic modulation characteristic of a nucleus losing integrity. It spun like an object content in its momentum, neither hurried nor anxious to tear itself apart. This quietness complicated the picture. If rotation had contributed to the breakup, it did so without the hallmarks of rotational overload. That meant the nucleus did not shatter because it spun too fast. Something else was at work, something in which rotation acted not as the primary force but as a whispering influence, a subtle contributor shaping how internal stresses aligned. One of the leading hypotheses focused on spin-axis orientation. A slowly rotating comet with its spin axis pointed at the Sun can experience extremely uneven heating. While the illuminated pole warms, the opposite pole remains in darkness. This arrangement creates a gradient not just across the surface but down into the interior, where temperature differences grow more pronounced with depth. If the nucleus carries pre-existing planes of weakness as spectroscopy and structural models suggested, then differential thermal expansion along those planes, combined with even modest rotational strain, can prime a clean fracture. Under this scenario, the comet's rotation did not cause the breakup. It guided it. Like a potter's wheel shaping clay, the slow spin moderated how stresses distributed across the nucleus. As sunlight penetrated deeper layers, expanding ices along a particular plane rotation gently tugged on the structure, coaxing it toward a boundary ready to give way. Not a tear, not a rupture, more like a patient unzipping and unravelling of tension stored in the ice over millions of years. But there was another clue hidden in the stability of the fragment's motion after separation. If rotation had played a significant role, the fragments might show signs of inherited spin differing rotation rates, irregular tumbling or angular drift as they adapted to their new shapes. Instead, their motion appeared remarkably controlled. Light curves suggested that both fragments rotated slowly with little deviation. Their spin states were calm, untroubled, almost coordinated. This coordination suggested something remarkable. The breakup preserved angular momentum in a way that produced balanced spins in both pieces. Such behavior is rare in violent rotational breakups. When comets tear apart under rotational strain, pieces inherit wildly different spin states, often tumbling chaotically. But in a gentle quasi-static rotational separation, one in which the nucleus slowly pulls apart along a structural boundary, angular momentum can be shared between fragments like two dancers separating but continuing the same movement. The fragments of 3i Atlas seem to embody this choreography. Models simulating such gentle breakup scenarios revealed a further insight. If the nucleus had a strong internal symmetry, whether geometric, compositional, or crystalline, then rotation could encourage a split along the symmetrical plane. The breakup becomes almost mechanical, akin to a rotating object parting along a pre-drawn line. The force required is surprisingly small. Even slight thermal expansion in the right region can trigger a division, if rotation is quietly pulling the nucleus toward that threshold. This led some researchers to explore whether 3i Atlas possessed a spin-induced stress field that gradually weakened the internal bonds over long timescales. In the deep cold of interstellar space rotation, however, slow acts continuously. Over millions of years, centrifugal forces, though faint, can influence grain alignment, pore geometry, and the distribution of microcracks. Even if the nucleus was cohesive overall, its long history of spin could have embedded subtle structural biases, directions along which the material was more likely to yield when warmed. If so, the breakup was not a sudden reaction to solar heat, but the culmination of a process that began long before the comet entered the solar system. The warmth merely revealed the fracture. Rotation sculpted it over time. But one more possibility lingered at the edges of the investigation, a scenario in which rotation was not merely a contributor, but the silent architect of the comet's internal evolution. In this view, the nucleus of 3I Atlas might have been a rubble body held together loosely, but shaped by rotation into a bilobed structure. Many comets exhibit this configuration, two lobes connected by a narrow neck. If the comet formed this way, or evolved into such a shape during its interstellar journey, the neck could have been fragile enough to split with minimal provocation. Slow rotation keeps such bodies stable under most circumstances, but slightest changes in internal temperature or composition can weaken the narrow junction. When this happens, the lobes gently drift apart, carrying their inherited angular momentum with them. This model elegantly explained multiple anomalies: the clean separation, the low debris, the stable rotation of fragments, and the symmetry of their motion. It suggested that 3I Atlas had always been two bodies, masquerading as one, its breakup merely restoring a natural duality sculpted by the endless patient spin of interstellar drift. But even this model could not fully explain the absence of debris. Rubble pile comets, when splitting, tend to shed particles from their necks. The clean divide of 3I Atlas implied that the neck, if it existed, was composed of material capable of breaking with surgical precision without scattering dust. This pointed again to unusual composition cosmic ray-hardened ices, or crystalline structures far more cohesive than those in local comets. Ultimately, rotation re-entered the narrative not as a dramatic force but as a quiet architect, an influence that shaped the interior of the comet over eons, aligning weaknesses, guiding stresses and orchestrating the conditions necessary for a breakup so delicate it left no trail. It was not a force that shouted, but one that murmured, working slowly in the darkness between stars, and in its soft whispering rotation may have provided the final key to understanding how 3I Atlas achieved the impossible, dividing itself with the poise of a celestial dancer, leaving nothing behind but two fragments moving in silent synchrony. By the time astronomers had exhausted every familiar mechanism, thermal stress sublimation jets, rotational strain, gravitational gradients, one possibility began to rise quietly from the margins of the discussion, a possibility that had hovered since the moment the comet was designated with its prefix 3I, the third known interstellar object observed passing through the solar system. Unlike native comets whose origins lie in the Oort cloud or Kuiper belt, interstellar visitors bear the fingerprints of foreign birthplaces shaped by conditions that may differ, not just slightly, but fundamentally from those in our own system. Their histories are long, their journeys vast, and their encounters unknowable. With 3I Atlas, the prospect of an unfamiliar origin carried profound explanatory power. It is one thing to study an object formed near a familiar star under the influence of a familiar radiation profile in a disk rich with the same minerals and volatiles that seeded Earth. It is quite another to confront matter shaped by an alien chemistry, by temperatures that never occurred in the solar system, by cosmic ray intensities far beyond local norms, by collisions or close stellar passes that rewrote its structure grain by grain. When scientists study an interstellar comet, they peer not only into the distant past of a foreign world, but into the physics of environments humanity has never directly sampled. And 3I Atlas behaved exactly like such a traveller. Its lack of debris, its immaculate split, its uncanny symmetry, its muted coma all pointed toward a body forged under conditions different enough that its structure, its ice chemistry and its internal architecture followed rules not yet written into cometary science. The first clue lay in the comet's super-volatile abundance. The ratios of carbon monoxide and carbon dioxide to water were higher than in most solar system comets. This hinted that 3I Atlas, formed in an environment colder than the region where typical comet nuclei develop perhaps at the far edge of a protoplanetary disk, where temperatures remain low enough for exotic ices to accumulate, or deeper still in a molecular cloud that birthed its parent star, where complex chemistry occurs at just a few degrees above absolute zero. In such environments, ices form differently. Water does not always crystallize uniformly. Organics may incorporate into ice matrices in ways that strengthen their mechanical properties. Carbon monoxide can freeze into layers far more brittle than anything in local comets. These exotic ices layered and interwoven through the nucleus could create fracture planes so clean that a breakup need not produce visible debris. But this was only the beginning. Interstellar comets endure cosmic bombardment for durations vastly greater than their local counterparts. The solar system's comets experience radiation from the sun, the occasional supernova flash, and cosmic rays filtered through the heliosphere. Interstellar objects, by contrast, travel unshielded through the galaxy, exposed to high-energy cosmic rays, with intensities that vary dramatically across space. These rays penetrate deep into icy structures, inducing chemistry that alters molecular bonds, rearranges crystalline lattices, and creates internal defects. Over millions of years, this bombardment may transform a comet's interior into a mosaic of radiation-hardened layers, some brittle, some unusually cohesive, some porous to a degree never seen in Earth's vicinity. Such structures are unlike anything observed in comets that formed and lived their lives within the Sun's protective magnetic bubble. The longer 3I Atlas drifted through space, the more its interior likely evolved. Cosmic rays could have annealed certain layers, turning loosely bound grains into hardened crystalline sheets. At the same time, radiation could have carved voids or created microfractures. Over epochs, these competing processes might have molded the nucleus into something simultaneously fragile and precise, ready to break along clean planes with almost no collateral scattering. Moreover, the comet's orbit hinted that it may have been ejected from its parent system through a close encounter with a massive body, a gas giant, a companion star, or a passing stellar neighbour. Such interactions can imprint powerful tidal stresses. These stresses deform cometary nuclei, embedding weakness lines into their interiors. Over time, the deformed regions may freeze into stable configurations, creating a natural fault line within the object one that can eventually reopen under the right thermal conditions. If 3I Atlas carried such an ancient scar, then the Sun did not create its breakup, it revealed it. The possibility that the comet originated in a binary star system made these scenarios even more compelling. Binary systems produce complex gravitational environments. Comets born there might form under tidal forces that stretch their interiors, aligning grains and volatiles in unusual patterns. They might also experience repeated passages through regions with dramatically different temperatures, producing layered structures unmatched by any solar system example. The idea of a foreign birthplace also illuminated the comet's dust deficiencies. If 3I Atlas formed in a low metallicity region, one where heavy element abundance was lower than the Sun's neighbourhood, its dust-to-ice ratio could be naturally low. Such comets would be composed largely of ices and organics, with minimal solid grains to scatter light during breakup. Their fragmentation would produce gas but little particulate matter, a direct match to the behaviour observed. And there was still more to consider. The sheer age of an interstellar comet may allow processes nearly impossible in shorter-lived solar system objects. Over hundreds of millions of years, ices can sinter, slowly fusing under faint thermal gradients. Organics can polymerize, linking into long, stiff molecular chains. Micropores can collapse, redistributing mass internally. These processes tend to make nuclei either more brittle or more cohesive depending on composition. Both outcomes could lead to an immaculate split if thermal or rotational stress is applied along the right plane. In this light, the breakup of 3I Atlas becomes not a violation of physics, but the natural expression of an object shaped by a galactic journey. Every oddity, every absence of dust, every sign of internal symmetry, every whisper of unusual chemistry reflects conditions that local comets simply cannot replicate. Its strange behaviour becomes part of a larger truth. The galaxy's diversity extends not only to stars and planets, but to the smallest icy wanderers drifting between them. And when such an object enters the solar system, it carries with it the memory of environments, processes, and histories entirely foreign to our own. Thus the question, why did 3I Atlas split without fragment trails, took on a new perspective. The comet may not have been capable of breaking the way local comets do. Its materials, its internal structure, its radiation history, and the stresses of ejection from a distant system may have combined to create a nucleus predisposed to split cleanly. What seemed anomalous was perhaps inevitable for a body shaped in the cold, ancient deep of another star's cradle. It was not simply a comet that broke silently. It was an emissary from elsewhere following rules written in a different corner of the galaxy, carrying within its fracture the quiet signature of its interstellar birth. By the time the fragments of 3i Atlas had drifted far enough apart to establish their own independent comet, the scientific community had already begun assembling a network of instruments dedicated to deciphering the mystery. The comet itself was retreating, sliding slowly outward from the sun's warmth growing fainter with every passing night. Yet the questions it raised only grew sharper. A split without dust, without debris, without the roar or spectacle of a typical fragmentation event demanded answers, and the tools designed to pursue those answers spanned continents and orbits, each probing a different facet of the fading visitor. The first wave of investigation came from ground-based telescopes equipped with wide-field imagers. These instruments, sensitive to faint brightness fluctuations, attempted to reconstruct the moment of breakup by comparing archival frames to the newly diverging fragment paths. Astronomers scoured data from Atlas, Pan-STARRS, ZTF, DCAM, any survey that had observed the region around the time the fragmentation must have occurred. Automated pipelines flagged anomalies while human analysts inspected the subtleties the algorithms missed. In these deep stacks of images, researchers hoped to identify the earliest hints of elongation, the faintest suggestion of twin nuclei emerging from a single point. Yet even with the most advanced image subtraction techniques, nothing definitive appeared. No transition frames, no blurred doubling of the comet's light profile, no dust haze preceding the discovery. The breakup remained concealed within the observational gaps, those unavoidable pauses when surveys turn their gaze elsewhere or clouds obscure the sky. This absence only magnified the enigma. The most important event in the comet's narrative happened silently, invisibly, leaving behind only the aftermath to examine. So scientists turned to the next set of tools, spectrographs. Instruments on large telescopes in chilly Hawaii, the Canary Islands, swept across wavelengths from ultraviolet to infrared, scrutinizing the chemical signatures of each fragment. These observations continued long after the comet's initial brightness faded, capturing spectra so faint they approached the limits of what modern detectors could pass. Researchers built models of sublimation rates, volatile compositions, and thermal evolution, attempting to compare the fragment's behavior with known comets. They ran simulations of how ices should sublime at various distances, what gas signatures should intensify after a breakup, how freshly exposed surfaces should behave. Nothing fit. The fragments remained quiet, emitting no sudden bursts of volatiles. Their spectral fingerprints stayed muted and steady. Even as they rotated into sunlight, no fresh activity bloomed, no spikes of water vapor, no surges of carbon monoxide, no hints of buried ices exposed by the fracture. The coma profiles remained narrow, subdued, almost disciplined. If the breakup had created new surfaces, those surfaces behaved with extraordinary restraint. Unable to draw answers from visible light alone, astronomers shifted toward instruments orbiting above Earth's atmosphere, where thermal and ultraviolet signatures could be tracked without interference. Space telescopes, those designed for planetary science as well as those for broader astrophysical targets, were repurposed briefly to observe the fragments while they remained accessible. The data these instruments provided were exquisite in precision, revealing small oscillations in temperature, slight deviations in reflectance, and soft thermal gradients across the surfaces. Yet even here the comet resisted easy interpretation. Thermal imaging showed no patch of exposed, unusually warm ice where fresh fracture surfaces should have been. No hotspot existed along the areas expected to have broken open. The fragments appeared as though they had always been separate bodies, their temperature distribution smooth and devoid of the disruptions one expects after structural failure. This was not merely unusual, it bordered on contradictory. For a breakup to occur, materials must separate. For separation to occur, new surfaces must be created. And for new surfaces to be created, those areas must respond differently to sunlight, warming faster, cooling differently, sublimating unevenly. But 3i Atlas displayed none of these signatures. The new planes of division, if exposed at all, behaved indistinguishably from older surfaces. This led to another phase of scientific investigation: numerical modelling. Teams used supercomputers to simulate how different internal compositions, structures and thermal behaviours could produce the observed fragmentation. Inputs varied: grain size distributions, porosity levels, volatile concentrations, crystalline alignments, cosmic ray-altered layers, internal voids. Researchers tested models where the nucleus was a cohesive monolith, and models where it was a fragile rubble pile. Models with bilobed structures and models with spherical symmetry. Models with exotic ices accumulated under deep interstellar cold, and models with unexpected internal temperatures. Despite thousands of iterations, only a handful of simulations produced breakups resembling what was observed: slow, silent separations with minimal debris. These rare, successful runs required improbable combinations of factors: a nucleus with uniformly distributed microcrystals, a deeply buried but coherent plane of structural weakness, a porosity profile allowing pressure to diffuse silently, and a sublimation environment that maintained thermal equilibrium across both emerging fragments. Such a configuration was unlikely in any solar system comet. But for an object shaped by millions of years of interstellar drift, such a structure, while still rare, became more plausible. The model suggested that 3I Atlas might belong to a class of bodies shaped by processes that have no analogue in local cometary populations. With simulations narrowing the possibilities, the final threads of inquiry turned to ongoing and future missions. Instruments like the James Webb Space Telescope, though not originally tasked with tracking faint comets, proved invaluable in modelling how exotic ices behave under solar heating. While JWST never observed 3I Atlas directly, the timing and trajectory were unfavourable. Its spectroscopy of other faint icy objects provided crucial analogue data. These comparisons helped researchers refine theories about how interstellar bodies might store release and restructure volatiles over long timescales. Meanwhile, planetary scientists drafted conceptual mission architectures for intercepting future interstellar comets. The idea gained momentum after the enigmatic passage of 1 Alaya Oumuamua and grew stronger still after the strange behaviour of 3I Atlas. Proposed missions included rapid response probes capable of accelerating to extraordinary speeds to rendezvous with, if not directly sample, interstellar objects. Designs featured dust collectors, volatile analyzers, impactor experiments, and even miniature landers. The hope was simple: if a future interstellar comet breaks, scientists want to be close enough to witness the event directly, with instruments that can detect even the faintest whisper of debris. In parallel, astronomers worked to refine the observational frameworks needed to catch future events in real time. This included adjusting survey cadence, expanding sky coverage, and improving automated detection algorithms. The challenge became not only to detect interstellar objects earlier, but to monitor them continuously enough to avoid missing the critical moments: the silent fractures, the subtle rearrangements, the transient events that carry the most scientific meaning. Through all these efforts, observational, computational, and conceptual, the mystery of 3I Atlas remained intact, softened only by the growing understanding that the phenomenon likely had roots in interstellar chemistry, deep cold physics and internal microstructures shaped long before the comet ever entered the Sun's domain. The tools of modern science had revealed the comet's behaviour with astonishing clarity, but had not yet unlocked the secret behind the silent split. Instead, they had illuminated the contours of the mystery, outlining where explanations might lie, and where the laws of cometary science may need to stretch. The fragments continued their outward journey, fading gradually as they receded into darkness. But the effort to understand them did not fade. Instead, it grew into a broader aim to prepare for what the galaxy might send next. Armed with instruments sharper, models deeper, and questions more attuned to the quiet signatures of interstellar matter, the search for answers had expanded beyond a single comet. It had become a campaign, a long-term scientific pursuit to decipher the hidden architecture of bodies born under foreign suns, to see in them the physics the solar system never taught us, and to recognize in their silence a new frontier of cosmic understanding. Across the arc of months spent observing 3I Atlas, from its faint detection to the slow fading of its twin fragments, astronomers were drawn again and again into the quiet emptiness the comet left behind, an immaculate void where dust should have drifted, where debris should have spoken, where the memory of a rupture should have been etched visibly into space. But silence prevailed, and in that silence, the scientific imagination found itself moving beyond physics alone toward deeper questions about fragility, impermanence, and the invisible forces that shape cosmic matter. The fragments continued outward on trajectories that now defined them as separate entities. Two worlds unbound, slipping gradually toward the deep cold that once shaped their parent body. Their motion, so calm and stable, carried an almost narrative resonance, as though the breakup had been not a violent interruption but a quiet act of becoming. They seem to drift like petals released from a long frozen bloom, each continuing a journey whose origins lay far beyond the sun's light. For scientists, their persistence raised one final philosophical tension. How can something so fragile survive a breakup so clean that it leaves no trace? Comets are the archetypes of cosmic impermanence, fragile, porous, easily shattered. And yet, this interstellar traveller demonstrated a form of resilience, as strange as its fracture. The pieces did not crumble further, did not erupt with delayed activity, did not peel apart under rotational stress. Instead, they maintained their form, their quiet sublimation, their restrained presence, as though the breakup had released them into a more stable configuration. This behaviour compelled researchers to re-examine the very concept of fragility in the context of interstellar matter. Perhaps fragility in bodies shaped beyond the sun's influence does not operate through violent decay. Perhaps interstellar comets are fragile in a different way, vulnerable not to shattering but to silent transformation. Structures so old, so deeply processed by cosmic rays and slow chemistry, might split not through destructive failure, but through internal reorganization. Their weakness may lie not in their inability to hold together, but in their predisposition to drift apart gracefully. The silence of the breakup became symbolic, a reminder that not all cosmic drama unfolds with spectacle. Sometimes the most profound transformations occur in quietness, in tension resolved without noise, in boundaries that part without tearing. Just as gravitational interactions can shape orbits without a collision, or cosmic rays can restructure molecules without leaving macroscopic marks, the universe often whispers its secrets through absence rather than presence. In this way, 3i Atlas serves as a reflection on the limits of human perception. Astronomers rely on brightness spectra, dust jet signatures that announce themselves through light. But the universe contains phenomena that elude these senses events, mediated through forces too fine or too cold to illuminate. The comet's silent fracture invites humility. There may be entire categories of cosmic behaviour that remain unseen, not because they are rare, but because they do not reveal themselves through the kinds of signals our instruments were built to detect. This realization turns the fragments of 3i Atlas into symbols of the unseen reminders that the galaxy is full of matter, shaped by histories we have not witnessed, sculpted by conditions we cannot yet replicate, transformed by processes we barely understand. Each interstellar visitor, fleeting as it may be, offers a glimpse into the unspoken architecture of other worlds. But their lessons are often subtle, encoded not in luminous displays, but in quiet contradictions. 3i Atlas's breakup without a fragment trail is one such contradiction. It challenges the language of cometary science, the expectation that all fractures must speak in dust and brightness. It reveals that the absence of evidence can be evidence itself, a signal of internal architecture sculpted under different rules. And it reminds us that the cosmos often moves in ways that escape immediate understanding, inviting us to expand our definitions of possibility. In the faint light of its receding fragments, the mystery becomes not a puzzle to be solved instantly, but a horizon to be approached gradually. Each silent comet, each dustless fracture, each peculiar interstellar visitor contributes a new thought to the growing tapestry of cosmic understanding. These mysteries become waypoints, gentle nudges that encourage science to stretch into unfamiliar territory, embracing not only the known but the possibility of the unknown. As 3i Atlas drifts back toward the interstellar sea, it carries with it a story written across millions of years, through environments the solar system never knew. The twin fragments fade, the coma dissolves, and the comet's once bright presence settles into darkness. Yet the questions it stirred remain luminous, glowing softly in the scientific imagination, urging humanity to look deeper, refine its tools, and prepare for the next whisper from beyond the sun's reach. And in that lingering quiet, the fragments become metaphors not only for cosmic emergence, but for our own fragility mirrors, reflecting the truth that understanding unfolds slowly in pieces through divisions that reveal more than they destroy. The universe is full of silent fractures, and each one reminds us that even in the absence of debris, a story endures. The story of 3i Atlas settles now into stillness, its fragments drifting into regions where sunlight thins, and the cold resumes its ancient governance. The instruments that once traced its faint glow have turned to new tasks, and the sky where its path once lay has returned to the quiet steadiness of distant stars. Yet its presence lingers like a soft imprint on thought, a reminder of the gentle mysteries that inhabit the spaces between worlds. In these final moments, the pace softens. The urgency of explanation gives way to something slower, something more contemplative. The questions raised by the comet no longer press with sharpness. They drift instead like dustless motes suspended in the mind. It becomes easier to imagine the silence in which the breakup took place, a silence deeper than vacuum, a silence shaped by time itself. There in the vastness between stars, the comet's long journey continues in calm inevitability. Perhaps its fracture was never an event at all, but a continuation, a quiet step in a story written across millennia. Its two fragments will wander through the galaxy long after this moment has faded from human memory. They will pass other stars, drift through other clouds, gather thin layers of frost, and carry forward the quiet physics encoded in their structure. Somewhere far from here they may warm again, and reveal new secrets or slip unnoticed through the darkness, untouched by any gaze. For now, all that remains is a gentle sense of wonder, an awareness that the cosmos holds mysteries subtle enough to escape even our finest instruments. In that awareness lies a kind of peace, a recognition that not all questions demand answers immediately. Some are meant to accompany us like distant lights on an unending night journey. And in that quiet, the fragments of Three-Eye Atlas fade softly into the dark. Sweet dreams.